Hi everyone, I'm Yibo from Peking University. My talk today is about our recent progress on VLSI placement, leveraging deep learning toolkit. We call it DREAMPlace. And this work is collaborated with UT Austin and NVIDIA. Modern VLSI designs are booming in sizes and complexity. It is easy to have billion transistor designs like NVIDIA's Xavier chip. The design is so large that we have to divide the chip into small partitions for backend design, with each partition containing 1 to 2 million cells. Even so, one iteration of the flow for one partition can take 1 week based on real industry information. Let alone there are hundreds of such partitions in the whole chip, and the flow needs to run many iterations. During the design process, placement plays a central role in the flow, as it is the first step in the design flow considering the physical locations of logic gates. The quality of placement can make huge impacts on design performance and closure efficiency, because the early stages require feedback from placement, and the late stages rely on high quality placement solutions for fast closure. Placement is a classic problem known as NP-hard and cannot be optimally solved. Furthermore, we also have to deal with extremely large design sizes, like 10 million cells with tough quality requirements. Therefore, people have been developing various efficient placement approaches to tackle these challenges. In this figure, we plot the recent progress in placement. From 2006, the placement quality has been improving. Current state-of-the-art results have been achieved by the ePlace family, which adopts a flattened nonlinear optimization approach. As the placement quality is always the top concern, we will focus on the ePlace approach in the rest of this talk. Let's first take a look at a general nonlinear placement formulation. The original placement problem can be written as a minimization to the valence objective while subjecting to the density constraints. The valence models the interconnection, and the density term penalizes overlaps among cells. A typical nonlinear placement algorithm relaxes the density constraints into the objective and iteratively optimizes using gradient descent methods. Although there have been many works trying to improve different nonlinear approaches, current nonlinear placers still have the challenges, including low efficiency, limited acceleration, and a huge development effort. For example, it takes RePlace more than 3 hours to finish a 10 million cell design, although Although there are some attempts to accelerate the placement engine, they either suffer from quality degradation or limited speed up. Moreover, it usually requires huge development effort for a placer like ePlace or RePlace. For example, it may take more than 1 year to finish the coding. With all these challenges, what does a dream placement engine look like? The dream placement engine should be ultra fast and produce high quality solutions. We also want to reduce the development overhead, such as from 1 year to several months, since the technology changes rapidly. A desired placement framework should also be easily extensible for new algorithms and acceleration techniques. While it might be hard to realize, let's first dream big. Let's make a concrete target here. Can we finish a 10 million cell design within 5 minutes without any quality degradation, instead of the current 3 hours? To realize our dream, we look into other areas solving similar nonlinear optimization problems, such as deep learning. In the past few decades, neural network training has achieved over 60 times speed up with GPU acceleration. Meanwhile, the performance of GPU grows exponentially compared with CPU. Moreover, There are a variety of toolkits available that runs on both CPU and GPU with easy-to-use APIs for deep learning applications. With all these achievements in deep learning, I cannot stop to ask a question. Can we leverage deep learning toolkits to develop our placement engine? Therefore, in this work, we present our DREAMPlace strategies. We propose a novel analogy by casting the nonlinear placement optimization into a neural network training problem. The DREAMPlace framework greatly leverages deep learning hardware acceleration like GPU and software toolkit like PyTorch, enabling ultra-high parallelism and acceleration while getting the state-of-the-art placement results. Next, I will explain how the analogy is established and how we developed the framework. To establish the analogy, we first briefly review the deep learning problem because the toolkit is originally designed for solving these problems. Consider the neural network a training problem. Giving any neural network with its trainable weight W, it takes the data samples as input and output prediction results, as well as errors during training. The training problem is essentially solving the nonlinear optimization consisting of two terms, the error term and regularization term for weights of the network. The optimization is done through gradient descent methods that require forward propagation to compute the objective and backward propagation to compute the gradient. This is a high-level description on the neural network training problem. Now let's look back to the placement. We can write the nonlinear optimization, placement optimization in the same format with two terms, a valence term and a density term. We can intentionally construct a virtual network that computes the valence with given each net instance as a data sample. The ground truth label for the net instance is set to 0. Then the output error is equivalent to the valence of this net. The intuition here about this construction is that ideally we want the valence of each net to be 0, as it is our objective to optimize. But in reality, there is always some non-negative valence values for each net, so which can be considered as an error. This is the conceptual construction of the one-layer neural network for solving the problem, so for solving the placement problem. Now we can solve the placement problem with gradient descent and perform forward and backward propagation. This analogy between neural network training and placement allows us to solve the placement problem utilizing the deep learning toolkits. Due to the large and open community, most toolkits provide functionalities like automatic gradient derivation, nonlinear optimizers, and basic linear algebra operators. What we need to implement is just the valence and the dense operators with high-level placement API. Of course, the efficiency of the operators is very critical to the overall performance of the placer. We will talk about efficient GPU acceleration to these operators later. To match the state-of-the-art placement engines, we also implement the same optimization algorithm in Python and legalization algorithm in C++. To implement the placement engine, we need to develop customized kernel operators for valence and density computation. The efficiency of these operators is very critical to the overall efficiency of the placer. Weighted average valence model is adopted to approximate the half parameter valence, which is rather complicated to compute the objective and its gradient. We develop a pin level parallelization with the CUDA atomic operations and achieved the 1.9 times speed up over the naive net by net parallelization. For the density operator, DREAMPlace proposed an analogy between a cell instance and an electric particle. Then the density penalty can be computed as the potential energy of the electrostatic system, and the gradient corresponds to the electric force. There are solutions to a well-defined Poisson equation and can be computed with a series of discrete cosine transformation and its variations. We propose a fast DCT implementation leveraging the highly optimized CUDA FFT kernel and shown 1.4 times faster than the native DCT implementation in TensorFlow. So far, our placer can only optimize for wire length and with density constraints, which may cause routability issues. For example, we may have a local congested region that demands for 5 by 4 tracks, but it only has 4 by 3 routing tracks available. Actually, DREAMPlace is very flexible to handle such routability challenges. We can inflate the areas of cells in the congested region and run several placement iterations with the new areas. Then the solver will spread cells further in the local region and satisfy the density constraints. And we can obtain 5 by 4 tracks eventually. To this end, we can establish an iterative flow for routability optimization with the help from a routing congestion evaluator, such as an external global router. Such a flow can be easily implemented in Python. Now we validate DREAMPlace on a Linux machine with 1 Intel CPU and 1 NVIDIA GPU. The state-of-the-art replace runs under a Linux machine with a 24-core Intel CPU. As the same algorithm was implemented, there is no quality degradation. We first evaluated on ISPD 2005 benchmarks and achieved more than 30 times speed up over multi-thread CPU implementation. We further evaluated on large industrial benchmarks, ranging from 1 million to 10 million cells. Over 40 times speed up is achieved. Eventually, for a 10 million cell design, we can finish it within 5 minutes compared with the 3 hours on multi-thread CPU. Here we plot the solving procedure for the largest ISPD benchmark, Big Blue 4, including the density map, electric potential, electric field, placement wire length, overflow, and the GPU utilization. We can see that the spreading process is rather smooth and the GPU utilization stays high. This indicates our implementation has a very high GPU occupation and did not waste much of the computational resources. We also validate the performance of Routability Optimization on DAC 2012 routability-driven placement benchmarks with 500,000 to 1 million cells. We can achieve 1%, even achieve 1% better scaled HPWL, which is a widely used metric considering both wire length and routability, compared with the state-of-the-art results from replace. Moreover, due to the native support to GPU acceleration, we can achieve 9 times speed up in global placement. Actually, during the global placement iterations, more than 75% of the runtime is taken by calling the external global router. Now we show a short review on the evolution of DREAMPlace. It starts from the original DAC version 0.0 to the TCAD version 1.0 with the routability optimization and the kernel improvement. Then in version 2.0, we add a GPU accelerated concurrent detailed placement engine, ASP-DAC, for ultra fast placement and refinement. Starting from version 3.0, we support a region constraint using a multi-electrostatic based algorithm, which can improve the compatibility and the applicability of DREAMPlace to more sophisticated designs. We further explicitly optimize routability by incorporating machine learning models into the placement objective. In DREAMPlace 4.0, we propose a timing optimization strategy with momentum-based net weighting. Recently, we also proposed a differentiable timing-driven placement engine to further improve the timing optimization by extending the analogy to multi-layer neural networks. If you still remember, we had a big dream at the beginning of this talk. We wanted to have a placer that can produce best quality. Now, DREAMPlace can match and sometimes even outperform the state-of-the-art placement quality in Y-length, routability, and timing. We wanted to have an ultra-fast placer. Now, DREAMPlace can achieve over 30 times speed up and finishes 10-minute cell designs within 5 minutes compared with the 3 hours on CPU. We wanted to develop placement algorithms easily. Now, DREAMPlace significantly reduced the coding effort with well-established deep learning toolkits. We also wanted to have highly extensible placer. Now, DREAMPlace decoupled the algorithm innovation and acceleration innovation. You can write high-level language like Python to develop algorithms and still get acceptable efficiency. This is what we did on the Routability Optimization. You can also devote to accelerating the well-defined kernel operators without worrying about mismatch in solution quality. When we look back, our dream has come true. Is this the end of the story? Not yet. Now it's time to dream even more. In the algorithm perspective, we can explore new gradient descent algorithms that are widely used in deep learning to further improve the quality. We can also extend the objective to consider detailed routability, incremental timing, macro placement, and so on. In the acceleration perspective, we can explore multi-GPU, distributed computing on CPU, and even mixed precision to further speed up DREAMPlace. The analogy between placement problem and the neural network training can be extended to other CAD problems, such as gate sizing, fixed outline, floor planning, etc. Let's keep on dreaming and make all dreams come true, because yesterday's dreams are today's science. You are very welcome to ask questions. Thank you.
Okay, thank you, Ivo. Yeah, I remember this slogan, dream bigger. Yeah, it's very good. Yeah, and also for your talk, you already mentioned the follow-up work after your TCAD paper. Yeah, so you have you even talk about the recent work that will be published at DAC 2022. Okay, thank you. Very, very wonderful presentation. So yeah, so Ivo, could you please look at the chat box? I think the Ziyang asked one question in the chat box. Can you take a look at this? And by the way, I see the KK Liu. Yeah, he raised your hand. I'm not sure if you want to ask a question. If you want, please leave your question in the chat box. Okay. So Ivo, please.
Yes. So Zhiyang asked a question about the stochastic optimizers, like those mini-batch based methods, whether they are useful in the optimization of DREAMPlace. This is a very good question. Actually, I did try that. If you take a look at our TCAD paper, because due to time limit, I didn't include them in this talk. So we tried momentum-based SGD and Adam, but actually we didn't try it in a stochastic way. So the reason is mostly because if we only grab a small set of nets, the optimization will be very unstable. But we didn't spend much time to tune the results. But from my observation, the optimization is very unstable. It is very easy to diverge. So in the end, when we adopt SGD or Adam solver, we will put all the nets feed all the nets to the solver, so and get the gradient. We found that by if we can have very good hyperparameters, they can even outperform the current solvers on some of the benchmarks.
Yes, yeah, I would like to follow up this question. Yes, like in your last slide, the previous one, I mean the Dreambigger one. So I think currently you have several applications, okay, on the timing, loadability, yeah. But like you mentioned, you maybe, yeah, you know, currently the deep learning, the advance of deep learning actually keep improving. So I just wondering maybe you can, yeah, consider a better way to enhance your framework, because I think it's really good that you put your tool, your framework on the GitHub open source for everyone. I think everyone can use it. So if you have a strong kernel, I think that would be even better.
Yeah. Thank you very much for the suggestion.
Okay. So Ivo, thank you. I think we already use our time. Okay. Yeah. So thank you for coming, and